Hi everyone, welcome to lecture 10. This is a short lecture on Newton's universal gravitational law and Kepler's law, and it's a combined lecture for both the calc and non-calc students. This is a historical aside, but it's still an important historical aside because I need to explain to you why Newton's laws have become so important today. And if we go back to when Newton developed this physics, this would have been in the 1680s. There were at that time there were other competing forms of physics like Aristotelian physics, and there was like these Neoplatonic physics ideas floating around, but they did not win out. Okay, they did not continue to today. Newton's laws won out, and even though today there's more advanced physics, like there's special relativity and general relativity and special relativity, and then there's also quantum mechanics. Newton's laws are still very applicable and they're still very accurate. They're not the final word in physics, but they're still very accurate. And they're very useful for things that are bigger than a molecule and smaller than a solar system. So that's quite a range, okay? You can't use Newton's laws to describe an entire galaxy, which is much, much bigger than a solar system. There you have to use general relativity. And you can't use Newton's laws to describe something like the motion of electrons inside an atom. That's too small, and there you have to use quantum mechanics. But that's from atomic size to the size of a solar system is a huge range, and human beings are within that range, and so that's why Newton's laws are basically the underpinning for kinesiology, which is the study of human motion, okay, of the motion of the human body. People that are into sports sciences and so on will study kinesiology, and kinesiology is all Newtonian physics. And you say, well, why do we use Newtonian physics and not quantum mechanics? And if the human body were smaller than an atom, then yeah, we'd have to use quantum mechanics. Or if it were bigger than a solar system, then we'd have to use general relativity. But we're in that range, that perfect range for Newton's laws to work. Okay, so what is it that Newton discovered that really kind of nailed it and said, yes, this is the correct physics? Okay, so at that time, that is in the 1680s and before, there was the problem of astronomy and how planetary motion worked. And going back to Ptolemy in the very ancient times, this is ancient Greece, they thought that the Earth was at the solar system and all the planets and the sun even revolved around the Earth. That kind of made sense because if you get up in the morning, you don't see the Earth moving, you see the sun rising in the east and setting in the west, and you go, okay, well then the sun is moving across the sky, it's not the earth moving, and you don't feel the earth move, so you go, well, how is it that the earth is moving? I don't feel it moving. So it kind of made sense. But then by the time of Copernicus, there was a problem with the calendar, and I won't go into this problem with the calendar, you can actually look that up. This is when the Gregorian calendar was eventually introduced, and to solve the discrepancies in the calendar, that is, year after year they were falling behind in terms of their dates. It was like Christmas was falling earlier and earlier in the year, and people knew this because they go, well, why is it so warm in Christmas? Okay, and you could compare it to the winter solstice, which is the shortest day of the year, and you could tell that December 25th was moving. And so they go, well, what's wrong with it? Well, Copernicus solved that problem, and the way he solved that problem was by saying, you know what, let's put the sun at the center of the solar system and make everything revolve around the solar system, including the Earth, and we'll give the Earth two motions. One motion is the Earth orbiting the sun, and the other motion is the Earth revolving on its axis. And with these two motions, he was able to predict very accurately how long a year was. And that's when Europe moved from the old Julian calendar, which was established by Julius Caesar, to the Gregorian calendar, okay, which is the calendar that we use today. Okay, you might find it interesting that the United States didn't actually switch from the Julian to the Gregorian until I think it was 1710. So, different countries switched at different times and the calendar was a mess. But pretty much everyone in the world now uses the Gregorian calendar based on Copernicus. So once again, Copernicus put the sun at the center, and he said the Earth goes around the sun, and the Earth also rotates around its axis. The usual picture you have of like the Earth's motion. All right. The problem with that is people said, well, how? I don't feel the Earth moving. I mean, it kind of works because it fixes the calendar, but I just don't get how this is possible because the Earth does. I don't feel the Earth moving, so maybe the Earth doesn't move. Well, Kepler actually used Copernicus's idea and improved it even more. He improved it to the point where he was able to predict planetary motion very accurately, which solved all of Ptolemy's problems and so on. And so it was so convincing to people that the sun really was at the center of the solar system and that the planets revolved around the sun, and that the Earth turned on its axis. That was so convincing to people that they weren't going to throw it out, but they just couldn't figure out how it was that the Earth could move. They needed a new physics to try to explain how the Earth moved because you can't feel it. And the person who first approached that problem was actually Galileo. And Galileo said, you know what, I can explain how the Earth is moving and you don't feel it, and I can explain all these things. And he did a series of experiments. He was the first real experimental physicist, okay? And you might even say he's the first modern physicist. And, he just produced so much material that was very convincing about, why the Earth really was moving around the sun and not vice versa. And it was confusing people because, they were still stuck in the old way of thinking of things, but it was pretty convincing. And then finally Newton comes along and says, you know what, I have these three laws, which are the three laws we just finished studying, the first, second, and third law of motion dynamics. And Newton said, you know what, with these three laws and one other law, which is the law we're going to study right now, I can explain all of planetary motion. And the insight Newton had with respect to gravity was that falling is the same force that causes falling is what causes the moon to go around the earth, which causes or also causes the earth to go around the sun, and so on. In other words, orbital motion and falling are really one and the same thing. Now, we usually say that Newton discovered gravity. Well, he didn't discover that things fall. What he discovered was that there's a universal force throughout the galaxy, throughout the universe, throughout the universe, that causes things to fall towards one another. Okay, and that's what causes the orbital motion. When he took his universal gravitational law, which we'll study in just a second, when he took that and used them with the dynamical laws that we finished studying, he was able to predict Kepler's laws. And that was it. That was the final step in really convincing people that this new physics was correct. Okay, and then the old physics just went away. No one studied it except for maybe for historical reasons. Okay, so how is it that falling is also responsible for orbiting? Okay, and this picture that I have here, sorry, I'm not very good at drawing, but the picture is sufficient. This actually comes out of the Principia Mathematica. It's a rough reproduction of what Newton actually drew in his manuscript. And the point of this diagram is to try to convince you that falling and orbiting are the same thing. So let's see how that works. So here we have the Earth. Okay, so you can see that ball is the Earth. And here, that little triangle there, that's a very high mountain. Okay, now, I mean, there's no mountain that's really that high, but so the height is exaggerated. But imagine that you're at the top of a mountain. Okay, so that dot right there where you see my cursor, that dot, that's you. And what do you have in your hand? A rock. And you throw it. Well, what's the rock going to do? It's going to fall. Now, if you don't throw it at all, it'll fall straight down. But if you throw it, it's going to follow a parabolic path, right? And so what I did is I drew this parabolic path. And so here it is, falling, 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 and then it hits the Earth, okay? So that little, follow my cursor to that little line in there, that's a short little segment of a parabolic path, okay? Now, if I throw the rock harder, well, it'll go further. Okay, but it'll still fall to the ground. And so that's my second line here. So you can see here I threw it, and it goes, and then it hits the Earth. Okay, now remember the Earth is curved, it's not flat. So now I'm going to throw it even harder, and it's going to go further, 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 further before it hits the Earth. Okay, notice the Earth is curving, so this thing is actually curving. The trajectory actually curves around the curvature of the Earth. Okay, but it eventually hits it. What happens if you throw it so flat, so hard, okay, that it's going to be falling, but it's always going to fall around the curvature of the Earth? So here it is. I've thrown it just a little bit harder, and now it's going to fall. It's going to fall. It's going to fall. It's going to fall, but it never hits the surface of the Earth, because as the trajectory curves, the Earth curves underneath it. And so it keeps falling, 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 and it just keeps going around and around and around, and you've achieved orbital motion. So the only difference between falling and orbital motion is whether or not the object hits the surface of the Earth. It's the same motion, okay? And so that's kind of surprising. I mean, a minute ago when I said that orbiting and falling were the same thing, you would have gone like, how is that possible? But, Newton here shows very clearly with a very simple little thought experiment that, if you're throwing something, when it's in the air, it's orbiting. It's just that it stops orbiting when it hits the ground. Okay. But if you throw it hard enough, because the earth is round, it'll just keep falling around the earth. And it just keeps falling around the earth, 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 and so on. Okay, and that's orbital motion. The moon is falling towards the earth, but because it has enough transverse velocity, it keeps falling, but it's not heading towards the earth. It just heads around the earth in a curve, around the curvature of the earth, and it never hits the earth. And there you go. Okay, now I don't know if you've ever been in an elevator that drops very fast, but you know how you feel lighter in an elevator when it starts to go down? The elevator in the Empire State Building is the one which is the most extreme that I've ever experienced, and also the Skyline Tower in Niagara Falls, Ontario. When that elevator first starts to go down, you feel like you're weightless, okay? Like it just starts to drop. And at that moment, when it's falling, you feel weightless, okay? When you skydive, when you first jump out before the air friction starts to get at you, you feel weightless, okay? So when you're falling, you feel weightless, okay? Oh, that's another thing is like the way they simulate zero gravity on Earth is they'll take a jet and they'll fly the jet really high, and then the jet will dive. And when the jet dives, and you know that if you've ever been in a plane, when it starts to go down, you lift up. But when the jet dives, you got about 30 seconds where this jet is just heading down and you're kind of weightless, so you can get a few seconds of weightlessness during the plane's falling, okay, controlled fall as it dives down, okay, and that's how you can simulate zero gravity on Earth. So when you're falling, you have this zero gravity, and when you're in something like the space shuttle, it's not that there's no gravity up there. In fact, there is gravity. I think it's like 8.9 meters per second squared at the height at which the shuttle used to orbit the Earth. Okay, that's not why the astronauts feel weightless. They feel weightless because they're falling. Okay, and so as the shuttle goes around the Earth, the shuttle and the astronauts within it are falling, and so they feel weightless within it. Okay, so this was all kind of like the brainchild of Newton, and Newton then, of course, had to put this into an equation, and he kind of guessed, but his guess was correct, and it turned out that later there was another physicist by the name of Cavendish who actually proved Newton's universal gravitational law. So there's no reason not to believe it. Newton's gravitational law has been superseded by general relativity by Einstein in 1915. But again, if you're not talking about things that are really, really big, like solar system size things, then you don't really have to switch over to general relativity. Newton's laws do a pretty good job, which is what we're going to discuss in the remainder of this lecture. Okay, so what is this universal gravitational law? And here it is. Okay, so what does this equation say? Suppose that you have two masses, m1 and m2, okay, and they are a distance apart of r squared. R. They're a distance apart r. So r is the distance between the two masses. Now the masses might be extended, so it's really the distance between the centers of the two masses. But we won't obsess about those details. So we got m1 and m2. These are two masses, and r is the distance between the center of these two masses. Okay. Then there's an attractive force between these two masses. It's always an attractive force, and it's given by this equation. You take the size of m1, multiply it by m2, divided by r squared, and then multiply by g, which is just a number. It's a number which kind of makes sure that the units work out for the universal gravitational law. And it's called the universal gravitational constant, and it's equal to 6.67 times 10 to the minus 11 meters squared divided by kilograms squared times newtons. Okay, so I wouldn't expect you to memorize that number. Our tests are open book anyhow, but I'll have those constants there so you don't have to go searching for them. It's not a number that's very easy to memorize. So back to the equation here, you multiply the two masses, divide by r squared, multiply by g, and that tells you the force. Now g, and this is MKS units, g is very small. 10 to the minus 11 is tiny, okay? Like 10 to the minus 9 is already billionths, like a billionth. So this is like 100 billionths of a unit. So, the gravitational force is actually a very small force. So you can have these two masses, and they're attracted to one another, but the force could be so small that you don't notice it. And that's what's happening in your day-to-day world. Okay, you don't feel, yourself attracted gravitationally to the wall or to your car or something like that. Like if you stand beside your car, you don't feel that your car is pulling you because of gravity. Okay, and that's because the mass of the car and and your mass are not that big. So if you calculate the force between them, they would be like probably into the less than micro newtons. Okay, absolutely tiny number. And so yeah, there's not going to be any noticeable force. But between you and the Earth, there's a sizable force. You can feel it, and that's your weight. Okay, and the reason you can feel it is your mass is not that big, but the mass of the Earth is huge. And so when you multiply the two numbers together, yeah, one number is not that big, but the other number is huge, resulting in a large number. And that's why you feel the force of gravity due to the Earth, whereas you don't feel the force of gravity due to your car. Okay, so yeah, this formula is correct, and it applies literally between any two objects in the universe, and you can measure it, but it's absolutely tiny. When I was in third year undergrad, I actually did the Cavendish experiment. Okay, it was an extremely hard experiment to do because the equipment had to be very sensitive. If you knocked the table, it would shake everything up, and then you'd have to start over. So it was a very hard experiment to do. But yeah, you could verify this, and it does work. So even between I think I had two balls which were about 100 grams each, two steel balls that were 100 grams each, you could actually measure the gravitational force between them. It's actually remarkable. Okay, so so there's Newton's universal gravitational law. Now, before we start using them, you say, well, what are we going to use them for? Well, what we're going to use them for is we're going to actually use them to prove Kepler's third law. Okay, so we're not going to do all three laws. The first and second law require calculus, and not only do they require calculus, they even require more calculus than even the calculus students have. They require some degree of vector calculus, and so we're not going to do that. Okay, I'll just expect you to know Kepler's three laws for planetary motion, and a little just not a proof, but a demonstration of the third law. You'll see when we do the examples towards the end. Okay, so Kepler, remember, he came after Copernicus, but before Galileo, and he basically discovered that the planetary orbits followed certain laws, and he did this by very accurate measurements of where the planets were at different times during the year. And these are the three laws he came up with. The first law is that planetary orbits are ellipses. They're not circles. They're actually ellipses, okay, with the sun at one of the two focal points. All right. So what I have here is a picture of an orbit. So this oval-shaped object here is an ellipse. Okay, not a very well-drawn ellipse, but there it is. It's an ellipse. All ellipses have two focal points. Okay, they're kind of like, how a circle has a center? Has one center, well, one special point, and the ellipse has two special points. They're two focal points, point A and point B. And if you take the distance, so you take any point on the ellipse, say this point P here, okay, and you measure the distance from P to A, and you measure the distance from P to B, and you add those two distances together, that is constant no matter where you put P on the ellipse. Okay, so the distance A, P, B is the same as, pick another point, call it P primed, A, P primed, B. Okay, so no matter where you are on the ellipse, you could pick a point here. If you add the distance from this point right here where my cursor is to A and this point here to B, you add those together, you're going to get a number, and that number is the same for the entire ellipse. Okay, the way you can make an ellipse, I don't know, like when you were kids, might remember making a circle by taking a pin, and then you would put a string, and then you would tie a pencil to the end of the string, and then, as long as the string was kept tight, you go around in a circle like that. Okay, well, you could actually do the same thing, but here you need two pins. So you put a pin at A, you put a pin at B, and then you tie a loose string between A and B. It's not tight between A and B. There's a little bit of play. And then you put a pencil in there, and you make sure that when you pull the pencil out, you keep the string from A to the pencil and B to the pencil tight, and then you just go around like that, and you allow the pencil to slip between the string. Okay, I don't know if you're getting the picture of this, but you got to allow the pencil to slip between the string, and the string is the distance A, PB. That doesn't change. And so as you move your pencil around and it's slipping between the string, yeah, the distance from A to P changes as you move P around, and the distance from P to B changes as you move the pencil around through the string. But the total A to P to B, that doesn't change. Okay, and there you go. There's an ellipse. So all of that was about an ellipse, but what Kepler said is that the shape of the orbits are ellipses with the sun at one of the focal points. So I don't care if you pick A or B. You say A is where the sun is. So, okay, and P could be like a planet, like the Earth. So the Earth goes around the sun like that, with the sun at one of the focal points. Not just the Earth, all of the planets do. Okay. Now, planetary orbits are very close to being circles, but they are slightly elliptical, and that means that the Earth is slightly further away from the sun during one point in the year than another point in the year. That's not the seasons. The seasons have to do with the tilt of the axis of the Earth with respect to the orbit of the Earth around the sun. Okay, but it is true that there's a slight the Earth is slightly closer at one time during the year and slightly further at another time of the year. Okay, and you can look that up. Like look up the perihelion of the Earth. All right, so that's the first law, that the planets are ellipses around the sun, and the sun is at one of the focal points of the ellipses. Okay, before I go on to number 2, let's go back to this picture right here, where we were looking at these trajectories. Now, when we did trajectory motion in 2D kinematics, remember, you would throw something up, it would go up and come down, and we had an equation for that. Turned out to be a parabola. So you would say, maybe these things are parabolic. Not really. That equation, when we did 2D kinematics under constant acceleration, assumed that the Earth was infinitely flat. Okay, so we don't live on a flat Earth. All right, despite what some people believe, we live on a round Earth, and so these are really not parabolas. They're actually ellipses. Okay, so when I taught you 2D kinematics, constant acceleration, and I said parabolas, they're very, very close to being ellipses. Okay, so it's not like I said anything wrong there. They are parabolas, but there's the parabola and the ellipses are so close to one another at that point because of the size of the Earth. Okay, and so in reality, when you throw something up and it comes down, it's really following an elliptical orbit, but near the surface of the Earth, it's very well approximated by a parabola. Okay, I just thought I'd mention that to tie this back into what we did earlier. Okay, so there's Kepler's first law, and on a test, just make sure that you know exactly what I stated in English, that the planetary orbits are actually elliptical with the sun at one of the focal points, and that's sufficient. Okay, so the second law is a little bit harder, but you see, the first law tells you the shape of the orbit. Let's look at it again. But it doesn't tell you how the planet moves along the orbit. Does it move at constant speed all the way along the orbit? Does it, speed up and slow down, speed up and slow down? If it speeds up and slows down, is there a rule for how much it speeds up or slows down? This is kind of like uniform circular motion, where I said, the speed was uniform along the circle. But here, it turns out that the planet's orbital speed actually changes. Let me scroll down a bit more. So here I drew again an ellipse. Okay, you can see here the two focal points. There's one focal point, and there's the sun at that focal point. There's another focal point there. I just drew it to show you that there are two focal points with the sun at one of the focal points. And what Kepler's second law says is that a planet sweeps out an equal amount of area in an equal amount of time along the ellipse. And you go, what does that even mean? Okay. So what it means is that if you take a planet here, okay, at one point in the orbit, and pick some interval of time. You could do a day, you could do a week, you could do a month. Okay, let's do a week, because within a week, it's very easy to see that a planet has moved across the sky at night. Okay, so we have a planet here, and we wait a week. The planet moves from here, where my cursor is, to right there. Okay, so the planet has moved along there. Now imagine that there's a line from the planet to the sun. And as that line turns, it kind of sweeps out an area. Okay, so here's the planet moving, and it sweeps out this area, which I've kind of hashed in there. Okay, and we can call that area A1. Okay, so that's the area swept out by the planet in 1 week at this point in the orbit. Wait till later in the year. Doesn't matter when, just later in the year. The planet is here. You once again wait 1 week. Okay, because that's your time interval, and the planet will move from there to there. Okay, all right. And again, it'll sweep out. The line from the planet to the sun will sweep out an area, and we can call that area A2. Okay. And if you measure area A1 and you measure area A2, you'll see that they're equal to one another. And that is Kepler's second law. That you could say a planet sweeps out an equal amount of area, but perhaps even more accurately than I've written here is a line from the planet to the sun sweeps out an equal amount of area in an equal amount of time. Okay. Now, at this point, you're still kind of like, I don't quite kind of get what that's really getting at. What does that mean about the motion? Well, when you're out far from the sun, so the sun is here, okay, ignore that other focal point, the sun is here. When the planet is out there, it's actually moving slowly, okay? And when the planet is over here, so here's the sun, when the planet is closest to the sun, it's moving faster, okay? So the way the motion goes is that out here, it's slow, and then it goes faster, 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 sweeps around here fast, and then slows down again. And then slow, 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 getting faster, 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 and then slows down again like that. So again, it's slowest, the planet moves slowest when it's further from the sun, and faster when it's closer to the sun. That's a qualitative way of stating the second law, and that's a good way to think about it. But in physics, we want to be very accurate. We want to do this mathematically, and so mathematically, you would just look at the area swept out by the planet in some fixed amount of time, and you'll notice that the planet always sweeps out the same amount of area in the same amount of time. Okay, and I think you can see why this would require some really fancy mathematics, because how in the world would you ever measure that area? Okay, you could do it just by construction paper, like with pencil and paper and stuff like that. You could like do this, and then you can cut out that area there and weigh it, and you can cut out that area there and weigh it, and see if the two weights are the same. If you were to transcribe the planetary orbit on, say, to some construction paper and do it that way. But using what's called vector calculus, you can also do this, but that's some heavy-duty math. Okay, so there it is. That's the second law, and it's very good at predicting where planetary motion, where planets will be. And I'm not going to prove that. Okay, and so here you can see in my notes, the closer the planet is to the sun, the faster it moves. Okay, which is interesting. That means that the Earth is actually moving slightly faster around the sun at one time of the year than at another time of the year. And here's what's interesting: the Earth turning on its axis doesn't change. Okay, but the Earth's speed along its orbit changes, and that means a day is slightly different. Like, you think that a day is 24 hours. Not exactly. It's slightly off. Okay. And I don't want to go into that. If this were an astronomy course, then we could go into that. But it turns out that there's this thing called a sidereal day and a solar day. And you can look that up if you're interested. What's the difference between a sidereal day and a solar day? Okay. And a sidereal day is how long does it take the stars to make one complete revolution around the Earth? And how long does it, and a solar day is how long does it take the sun to make one complete revolution around the Earth? Okay, not that the sun is revolving, but appears to make one complete revolution. And you'll discover that the time it takes for the stars to make one revolution and the time it takes the sun to make one revolution are different. Okay, and I'll let you look that up if you're interested, and you can see why that is. And by the way, that was the clue that allowed Copernicus to fix the calendar and to what we have now, which is called the Gregorian calendar. Okay, all right, let's move on to the third law, because the third law is really the interesting one, and it's the one that we're actually going to do problems with. The third law says if planet 1 is orbiting has orbital radius r1 and orbital period t1, and planet 2 has orbital radius r2 and period t2, then the following relationship holds. Okay, so if you take the radius of our planet 1, the radius of the orbit of planet 1, r1, and you cube it, divided by the period of the orbit of planet 1, and you square that. So it's r cubed over t squared for planet 1. That's the same for r cubed over t squared for planet 2 and for all the planets. Okay? So why is that? Why does it turn out that if you take the radius of a planetary orbit and you cube it, and you take the period of the orbit and you square it, you take that ratio is the same for all the planets? Okay, well, I'm going to actually prove that for you, but I should tell you before we move on that this is a slightly doctored up version of Kepler's third law. And the reason is I just finished telling you that the planetary orbits are not circles, and they're ellipses. And there's no such thing as a radius for an ellipse because it has two focal points, okay? Well, I guess you could say the average radius here. But for what we're going to do is, because again, I don't want to get into all the heavy-duty math, I'm just going to prove Kepler's law for the special case of a circular orbit. So circles, all circles are ellipses, although not all ellipses are circles. As the two focal points are brought together on an ellipse, the ellipse becomes more and more circular. Okay, and the planetary orbits, they're not exactly circles, but they're very, very close. Okay, the measure of the deviation from circular is called the eccentricity, and the eccentricity of the planetary orbits is very small. Okay, there are other things that orbit the sun, like comets. Comets have huge eccentricities. In other words, they're like ellipses, but they're like these very long ellipses. Okay, and remember the second law says that the closer something is to the sun, the faster it's orbiting. That's why, comets, when they actually approach the sun, that's when they start to glow and they approach the sun. We only see them for a few months because they whip around the sun for only a few months. But then they get thrown way out into the solar system, and out there they're moving very, very slowly, according to Kepler's second law. And so they'll spend hundreds of years way out in the distant reaches of our solar system, and then they'll come in, and when they come in, they zip around the sun really fast because Kepler's second law says the closer that comet is to the sun, the faster it'll move. I've only seen a comet once in my lifetime, and I forget the name of the comet. It wasn't Halley's, but it just looked like this really interesting triangular cloud in the sky. It was white, and we only saw it for a few weeks, and then it was gone. And that the reason being is that it's just in the vicinity of the sun for a couple of months, okay, and then it's gone, okay. And of course, it's near the sun a couple of months, but it might be only visible in the night sky for a couple of weeks. So it was a very rare, it's a very rare event. But this comet, is probably out there right now, and it's going to take hundreds of years before it comes back. All right, let's prove Kepler's third law. So here we go. So again, if we form the ratio r cubed over t squared for one planet, and you form the ratio r cubed over t squared for another planet, you'll find that they're the same. Okay, and you could do this for all the planets in the solar system, and they'll turn out to be the same. Okay, so why? All right. So again, I'm just doing this for the special case of circular orbits. Let's just look at planet number 1, and the math for planet number 2 is going to be identical. So we're assuming a circular orbit. So here's the orbit as a circle, and it has a radius r1 and a period of motion t1. Okay, so this is uniform circular motion. If you go back to the equations that I gave you for uniform circular motion, you'll see that the acceleration, the centripetal acceleration, was given by this formula, 4 pi squared r over t squared. And there it is again, with just a couple of differences. First, here I'm calling r capital R instead of lowercase r, but it's still the same r, meaning it's still the radius. And I had to put the subscript 1 because in a minute I'm going to do the same thing for planet 2. And there, you're going to have A2 instead of A1, and you're going to have R2 instead of R1, and so on. Okay, so so there you go. You've got a planet going around a circle at the constant velocity, and so you have uniform circular motion. And with uniform circular motion, the acceleration is expressible in terms of the radius and the period by this formula right there. Okay, the next question you ask yourself is, what's causing this acceleration? Okay, remember, in the absence of any acceleration, Newton's first law says things will just keep going in a straight line. But no, this object is turning. So something is causing it to turn. Something is causing it to accelerate. And the answer is gravity. The gravity of the sun causes the planet to turn in its orbit. If so you could somehow magically turn off the sun's gravitational pull like that, all the planets would stop orbiting and then just continue in a straight line, and who knows where they'd wind up in the galaxy. Okay, but no, the sun's gravity keeps turning the planets, so that they keep turning around the sun. Okay, so what's causing that? Gravity. Gravity is causing the centripetal acceleration. Okay, now if gravity is causing the centripetal acceleration, we actually have two equations that we can use. One of them is Newton's second law. And Newton's second law basically says that the force of gravity is going to equal ma. All right, but here I said M1A1 because it's the mass of planet 1 multiplied by the acceleration of planet 1. So if you take the mass of planet 1 multiplied by the acceleration of planet 1, you're going to get the force on planet 1. That force on planet 1 is the gravitational force that's causing the circular motion. All right, so the other equation we have, which we can replace that Fg, is we could say, you know what? The force of gravity, yeah, according to the second law, it's equal to M1A1. But how do I actually calculate that force of gravity? And we have a formula for that. That's Newton's universal gravitational law. So I'm going to take out the force of gravity using the universal gravitational law and replace it with G, the universal gravitational constant, M1, that's the mass of planet 1, MS, which is the mass of the sun. I mean, I could have called it M2, but I've got another planet called M2. So I'm going to call the sun MS divided by R1 squared. Okay, so there's the force of gravity, the universal gravitational law. Okay, that's got to equal M1, so that's still there from the equation. And for A, I'm going to replace it with its centripetal acceleration formula there like that. Okay, that comes out of uniform circular motion. So what went into creating this equation here, so the first equation was Newton's second law. So starting from Newton's second law, for the force, we used universal gravitational law, and for the acceleration, we used uniform circular motion. Okay, and just remember that the two masses here are mass of planet 1 and the sun. Okay, now the M1 actually cancels out. Let me just show you that quickly here. See that M1 there and that M1 there? They actually cancel out. And so all you get is that G ms over R1 squared is equal to 4 pi squared R1 over T1 squared. Okay, and now all I'm going to do is just do a little bit of algebra here. Basically, I'm going to, over here, I'm going to multiply both sides by R1 squared, okay, and then divide both sides by 4 pi squared. And what I wind up getting is R1 cubed over T1 squared. So that looks promising because that's one of the sides in Kepler's law. So I get R1 cubed over T1 squared. Okay, we can call that equation A there like that. Look at what's on the left-hand side though. We've got G, and what's G? Just a constant. What's ms? That's the mass of the sun, which is the same for both planets. And 4 pi squared, that's also just a constant, okay? So the left-hand side of this equation is just a constant, and the right-hand side is R1 cubed, the radius of planet 1 cubed, divided by the period of planet 1 squared, okay? And so that's a constant on this side here, and that's equal to this ratio. R can change, but T has to change with it, such that the 2, when you cube R and divide it by T squared, has to remain the same, has to remain constant. So if we repeat this entire thing for planet number 2, I'm not going to redo that because everything would be the same except that instead of my subscript 1, I'd have subscript 2. And so I'm still going to get G, the universal gravitational constant. That's the same for both planets. I'm going to get ms, the mass of the sun. That's the same for both planets. On the bottom, I get 4 pi squared. That's just a constant. And on the right-hand side, I get R2 cubed divided by T2 squared. Well, if we just eliminate the left-hand side of both of these equations, we can bring them together, and we just have that R1 cubed divided by T1 squared is R2 cubed divided by T2 squared, and that's the proof. Okay, that kind of proves it. Now, the reason I wanted to do this is even though it was a pretty big deviation from the ellipses, it still shows you that the universal gravitational law, okay, that's that G m1 m2 over r squared, and the centripetal acceleration together actually give you Kepler's third law. Okay, now Newton actually did this. Newton did this, and when people saw this in his work, they go, oh yeah, he's got it. He's got these 3 laws which are easily provable on Earth. The first law about no acceleration if there's no net force. The second law is F net equals ma. And the third law, if object 1 exerts a force on object 2, then object 2 exerts a force on object 1. If you take those 3 laws, which apply everywhere, they don't even, not just gravity, they'll apply even on Earth. They apply to all those blocks we had going downhill. Okay, so you take those 3 laws, and then you add this third law, which says, there's just this attraction between objects in the universe, and it's gm1 m2 over r squared. Boom, you get Kepler's laws. Okay, you get all 3 of them, but I just showed you for the third one. All right, so there's the theory, and on a test, you say, what would you have to know? Well, on a test, you should be able to at least state Kepler's first, second, and third law verbally, okay, and then be able to do the problems that I'm going to show you right now, okay. So here's the first problem, and my first problem says, look, the Earth has a radius of 6,371 kilometers. You could just Google for this. Just Google the radius of the Earth. That's what I did to get that number. Okay, so it has a radius of 6,371 kilometers, and it has a mass of 5.972 times 10 to the 24 kilograms. Okay, so that's pretty heavy. So there's the radius of the Earth and the mass of the Earth. Show that the acceleration due to gravity, and I should have probably said at the surface of the Earth, but it's kind of understood here. Show that the acceleration due to gravity is 9.8 meters per second squared using Newton's gravitational law. I mean, I've just given you two different ways of calculating gravity at the surface of the Earth. I've given you F is equal to mg, all right, which is what we've been using up till now. You just take m and you multiply it by 9.8 meters per second squared, and you get the weight of the thing, all right? Well, we've been approximating 9.8 as 10, but you got the idea, okay? But now I've given you this new way of doing it using universal gravitational law. They better not be in contradiction. They better both give you the same number. So that's what this problem is about. Let's see that, okay? So the weight of m1, which is this mass, okay, or some mass, m1, at the surface of the Earth is going to be given by, well, if you use one way of doing it, it's m1g, right? So, just remember the problems we did where we had these, masses and they were sitting on table, and the first question I said was, what's the weight of this thing? What's the force of gravity on this thing? And we would say, okay, the force of gravity is equal to mg. Okay, so there it is, mg. But I put m1 here because I've got two masses going on, the other mass being the mass of the Earth, okay? So m1g, that's the weight of m1 here at the surface of the Earth. There's another way to calculate the weight, and that is g multiplied by the two masses, m1, and I call this me for mass of the Earth. So what I had above is m2 is basically mass of the Earth divided by re, and what's that? That's the radius of the Earth. And the reason it's the radius of the Earth is because if the mass is at the surface of the Earth, then the distance from the middle to the mass is just the radius of the Earth, okay? And so there you go. This is basically the old way of calculating the weight of something at the surface of the Earth, and this is the new way of doing it, okay? Notice that m1 cancels, and so you just get on the left-hand side, you just get g, little g, okay? And that's got to equal capital G, mass of the Earth divided by the radius of the Earth squared, okay? So we have g is equal to capital G me over re squared. If we replace g with its MKS value of 6.67 times 10 to the minus 11, okay? And then me was the mass of the Earth. That was that 5.972 times 10 to the 24th. The radius of the Earth, you're going to have to square it, but above I gave it to you in kilometers, so you have to multiply by 1,000 to get it into meters. Remember, this has got to be an MKS. And the rest of it is just crunching it through your calculator. And if you crunch that through, you get that, as expected, 9.813 meters per second squared. So I kept a few extra digits there just to, make sure that you could see that it actually turns out to be 9.8. But yeah, there it is. Okay, so these two methods of calculating the force of gravity on an object, its weight at the surface of the Earth, are identical. But I think you would agree that just doing mg is much easier because you're just multiplying by one number. This, why would you ever want to use this? You wouldn't use it at the surface of the Earth. You would just use mg at the surface of the Earth. This is for like when you're in other places in space. Like, like if instead of saying at the radius of the Earth, suppose I'd said twice the radius of the Earth. Well, at twice the radius of the Earth, you're not going to get 9.8. You're going to get much less. Okay? And so that's when you would want to use this. When you would want to use the universal gravitational law when you're not at the surface of the Earth, whereas you'd want to use mg when you are. Okay? So there's our first problem. Here's our second problem to illustrate Kepler's third law. Mars's orbit is 50% further from the sun than the Earth's orbit. Okay, so the Earth has an orbit. Mars's orbit is going to be 50% bigger in radius. Okay, how long does it take Mars to orbit the sun? Okay, in other words, how long is a Martian year? All right. Now, for these problems, you don't actually have to use the radius of the Earth's orbit in MKS units. Okay, now normally MKS is a good way to do it, and it's like foolproof. If you're not sure, switch to MKS. But for this particular equation here, let's go back to it. this particular equation right here, you really don't have to switch to MKS. As long as you work in the same units, because as long as you're using the same units for R1 as R2, so the same units for R1 and R2, then the units will drop out. And use the same units for T1 and T2, they'll drop out. So you can measure T's in minutes, you can measure T's in hours, you can measure T's in days, you can measure T's in Earth years, or so on. You can measure R in meters, kilometers, whatever. Again, as long as the two R's are in the same units and as long as the two T's are in the same units, it'll work out. So what I did in this problem, and this is very typical if you take an astronomy course, you don't use the distance from the Earth to the Sun in meters or kilometers. You use what's called an astronomical unit. And the distance from the Earth to the Sun is exactly 1 astronomical unit. And the reason is because we defined it that way. The distance from the Sun to the Earth is 1 astronomical unit. It's very useful for measuring distances in the solar system, so you don't have to say like millions of kilometers and things like that, okay? So 1 astronomical unit, again, the distance from the Sun to the Earth is 1 AU, 1 astronomical unit, by definition, okay? Just like the kilometer was defined a certain way, a meter was defined a certain way, we simply defined an astronomical unit to be 1 astronomical unit distance from Earth to Sun. Okay, now if the distance from the Earth to the Sun is 1 astronomical unit and Mars is 50% further away, then that distance is going to be 1.5 astronomical units. Okay, and so RE is 1, RM is 1.5 in AUs. Now you could use 1 Earth year, but I decided to use days. How long does it take the Earth to go around the Sun? 365 days. Technically 365 and a quarter days, but I'm going to use 365 there for this problem. And the question asks, how long is a Martian year? It's TM there like that, okay? So there's nothing much more. You just substitute the numbers into this equation and solve. What I did is I isolated a TM because that's what we want to solve for. So I had, originally I had RE cubed over TE squared is equal to RM cubed over TM squared. Multiply both sides by TM squared, divide both sides by RE cubed, and it gives you this formula here. Well, here I have a TM squared, okay? So TM is isolated on the left-hand side, but squared. Take the square root of both sides. That reduces to the square root of RM cubed divided by RE cubed, okay, all under the square, multiplied by TE, the period of the Earth's orbit. Putting in the numbers here, 1.5 cubed divided by 1 cubed, take the square root of all that, then multiply that by 365, and you get 670 days, okay? So an Earth year, that is the time it takes the Earth to make 1 complete revolution around the Sun, is 365 days. The time it takes Mars to make 1 complete revolution around the Sun is 670 days. Okay, so that's it for this lecture. A little bit of a historical aside, but you could see that, you know, when Newton finally published his work and people saw how incredibly accurate it was in terms of describing motion on Earth and motion in the solar system, people realized that Newton had basically, you know, solve the problem, okay? Since ancient times, people wondered how the planets and the celestial objects move. Well, Newton solved it, so that made him famous, and that's why his physics persists to this day. All right, thank you.